Okay, so the Biasvariance trade-off. Let's see. Okay, so the way people normally trade off bias and variance is by looking at the mean squared error. Okay, so that's MSE. And that's going to be a function of H. And we're going to choose H to minimize the, it's actually the asymptotic mean squared error. Okay. And for now, like, we don't really have to worry about the constant terms. I mean, you kind of saw what they correspond to. But let's just focus on H. These constant terms are going to be functions of like the density and the derivative of the density. Those were the things where we said it was bounded by this or that. So for now, let's just focus on the H, you know, and I'll just put in the what we derived out before. Okay. So this is the bias. The bias depended on H, but if we square the bias, I mean, I guess technically this would be like C squared, but in the notes I just put C. So it's, let's just, we're abstracting kind of from what the constant terms are. So this is going to be bias squared, okay, and this is variance. Okay, so take the derivative with respect to H, and you'll get, and we'll come up with an optimal H as a function of N. Okay, so it's going to be 2CH minus C prime over NH squared equals 0. So 2CH equals C prime over NH squared. So we get H to the cubed equals, let's see, this is a 2. H to cubed equals C prime over 2C n to the minus, oh, and then we take the cubed root. So this is the formula, and this is also going to be to the 1/3. So it tells you the optimal rate. So if I wanted to trade off bias and variance, this tells you the rate at which I should, you know, have H going to 0 as a function of N. So remember, like 1 over N, the square root of N works, but this says that the optimal H that trades off. So the reason we square the bias here, well, first of all, it's just a definition of mean squared error is always bias squared plus the variance. So for the OLS estimator, what would the mean squared error be? So what is the bias squared for the OLS estimator? So think about, like, did the OLS estimator have a bias? Yeah, OLS is blue, right? OLS is best linear unbiased estimator. So for the OLS estimator, we only have a variance. So the mean squared error is equal to the variance. Okay, so for the OLS estimator, there's only this, and this would be 0. But for a biased estimator, and this is a biased estimator, sometimes bias estimators, even in regression analysis, they sometimes use bias estimators because, I mean, sometimes they could be more precise, you know, and especially if the bias goes away, it then gets large. You know, you might not be that concerned about bias if you have this trade-off that the variance is lower. Okay. So this is how you choose H. And so there's actually a big literature about how you choose H. H is called a bin width binwidth, bandwidth. There are a bunch of different names kind of for the same thing. So it just, if you read some of these articles or something, I mean, you could go, look at some of the original articles. I didn't put it on the webpage because I'm not expecting you to do that, but this is called the, well, this is the histogram version, but the kernel density estimator in general is called the Nadaraya-Watson kernel density estimator. Okay, and this was really developed in the statistics literature. The economists use these methods a lot, but the original papers, I think this paper was written in the 1950s. So they have both a density estimator and a regression estimator. All right, so this is, and there are tons of papers about bandwidth selection as well in different types of models. Okay, so this, and this is one approach, is to minimize the asymptotic mean squared error. All right, now let's look at another way you can do the histogram estimator, which actually will improve the performance of the estimator, kind of surprisingly. Just like a simple thing you can do to make it perform better, okay? So suppose instead of doing the bin like we were doing it before, we now look at x naught plus h and x naught minus h. Okay, so we do, so the width here would be 2h. And this is symmetric binning. So if we want to know the density value at x naught, we do a bin symmetrically around x naught, like plus h and minus h. Okay. Okay, so Omkar had a question about the C and the C prime. So actually, yeah, those were upper bounds the way we had it. If you would actually choose the optimal bandwidth, you wouldn't plug in the upper bounds. You would actually have the values of like f of x naught or f prime of x naught. So what's normally done, I mean, you might think it's a little bit odd because you're trying to estimate f of x naught, and you need to get a bandwidth to do that estimation. And then when you derive out the formula for the optimal bandwidth, f of x naught and f prime of x naught appears in the formula. And that's what you were trying to estimate to begin with. So what they normally would do is use like a non-optimal bandwidth to start with. Or even what some people do is and this is actually a very common procedure, they assume a parametric distribution to start with. So for example, you could say f is normal. You get kind of pilot estimators of the density, and then you use those initial estimators to get the optimal h. And then you redo your density estimates. Okay, that's how, and that's actually a very famous bandwidth selector. So you might see it even in some software. They call it the Silverman rule of thumb method. Okay, and this is where actually Silverman had a whole book only on kernel density estimation. Silverman has an entire book. It's a statistics book. But the Silverman rule of thumb estimator initially assumes like a normal distribution, gets a pilot bandwidth, plugs in the pilot bandwidth, gets the optimal h, and then redoes the estimation. Okay. And there's actually a pretty large literature. Like you could take a whole course probably in bandwidth selection, because there are a lot of different competing methods. Okay, like some of them actually have like fixed points, they derive out like optimal bandwidths. Because if you have this function for h that's a function of f, well, f and f prime, you can actually solve that as like a fixed point. So it can get pretty involved actually. And But luckily, a lot of the leading bandwidth selectors are available in R, actually. Because usually when people come out with a new method, they write some R code. Try, you know, to make their own method more popular, they want to make sure it's easy to use. Okay, so this is symmetric binning. Okay. So this little modification, it turns out, improves the performance of the estimator. So we can write the equation for f hat of x naught as 1 over nh. Okay, and this could be indicator for, let's see, x naught minus xi less than 2h. Okay, is it less than 2h? Yeah, so the width here is 2h. So this would add up all the observations. Let's see. X naught was, maybe I'll write it. I guess it didn't look that intuitive probably, but this is indicator for xi member of it's x naught minus h and x naught plus h. Okay, and then we can write this as, yeah, this should be 1 over, let's see, 1 over n. I don't know if this is easy to see. Okay, well, we can write it this way, okay, which is like equivalent. So 1 over nh times 1/2 indicator for x naught minus xi over h is less than 1. Okay, so you can plot what this looks like. This is S. So if I plot S at 0, 0 to 1, this has a height of 1/2. And anywhere else, it drops to 0. That's what the histogram estimator looks like. Oh, let's see. Why did we divide by? It's h in the previous inequality, which okay, let's see some questions. Why do we divide by nh instead of 2nh? Well, here's the 2. Well, the width of the bin here is 2. Oh, maybe the width is, oh yeah, this is where the 2's missing. Actually, this should be 2 because the width of the bin is now 2h. So this should be like n times 2h. Okay. All right, so this is what this function looks like. And this is called a kernel function. Okay, and this is actually an example of a uniform kernel. Because this is, and it integrates to 1. So this is actually a proper density. This is the uniform kernel density. Okay, so instead of doing the uniform kernel, we could also consider alternative kernel functions that have more of a bell shape. You know, because the uniform kernel puts a weight of 1/2 on all observations, you know, within a certain distance. Every observation gets the same weight. But you could also have a different kernel function that puts more weight on observations that are closer to x naught. Because I want to learn about the density at x naught, so it might make sense to put more weight near x naught. Okay. So we can actually have a kernel function that's doesn't necessarily have this, you know, uniform shape. It could have more of a smooth shape. Okay, so there's actually a whole family of kernel functions that would work. And the general form for the kernel density estimator, and we'll see like what are some requirements for a kernel function to be good. Okay, but this is the general form for the kernel density estimator, and it includes the uniform kernel. You can always do that one if you really like that one. So that would be like a special case. Okay, we're just going to write it in more general notation. Okay, so that's the general form. But of course, I could choose K to be this if I wanted to, right? And we'll look at like, but the key point relative to the histogram estimator is that now we're doing K symmetrically around the point x naught. And that symmetry you'll see, we can actually see why it's better. Like what makes it better to have it be symmetric. Okay, and it turns out that symmetry decreases the bias. Okay, so some examples of K functions. So there's maybe like maybe 8 different kernel functions or so that people use. I use this one sometimes called the bi-weight kernel. So it's 15/16 times s squared minus 1 squared if s is less or equal to 1, otherwise it's 0. So this is called the bi-weight kernel, but some people call it the quartic kernel. You know, I'm not sure. This part of the challenge in this literature is that there's so many different names for the same thing. So you have to be a little flexible. Like some people call this the quartic kernel. This kind of looks like a normal distribution, except it drops to 0. You know how the normal is never 0, even out in the tails it's something positive. But you could also use the normal. So you could use the normal PDF. That turns out to be another valid kernel. Even though the tails never actually drop to 0, I mean, they're very low, but the normal kernel would actually give positive weight to all observations, but the weight would just be a lot lower if it's further from the point x naught. Okay, so what we're going to do next is derive out the bias for this general kernel representation. And this is what's called the Nadaraya-Watson kernel density estimator, this estimator. And we're going to look at the bias. Okay, and the techniques are similar, like where you do this Taylor expansion. So E of f hat of x naught is, so this 1/n is going to cancel with the n terms, you know, because everything's like independent. So this can be 1/h, okay, k of x naught minus xi over h times f of xi dxi. Okay. So what I'm going to do is a change of variables, actually. And it just makes things a little easier. So I'm going to say S equals x naught minus xi over h. Okay, so S times H is equal to X naught minus Xi. So ds times H is equal, because X naught is just a constant. So the random variables are S and X here. So this is equal to minus dxi. So this is like H times ds. And we're going to change out, so we're going to, wherever we see this, we're going to put like S. And so xi by itself is going to equal to X naught minus sh. So I'm just going to rewrite this equation, changing the variables in terms of S. Okay, and then the other thing you need to notice is when xi is minus infinity, S is positive infinity. So you also have to change the limits of integration. Okay, so we've got like 1 over h. So I'm going to write here positive infinity minus infinity, because we're writing in terms of S. Okay. And then where I have dxi, it's minus h times ds. Okay. I know at first this might look like it's hard. I realize that it's kind of new. Okay, so probably you never had experience. I mean, that's why I want to show you, because it's kind of new stuff. It's, you know, modern econometrics. I mean, even though these initial papers were from the 1950s, but people work on these estimators, you know, now even. Like some of the bandwidth selectors, every year they come out with new ones. So well, that's a pretty. So don't worry if it doesn't look, you know, staring at it, I realize it might look kind of hard, but if you kind of sit down with pen and paper and just go through it once yourself, because the same techniques are used over and over. So you just have to kind of get used to it a little bit. Okay, now this H is going to cancel with this H, okay? And this minus sign, we can actually change back the limits of integration and get rid of this minus sign. Okay. All right. And so now we're going to work with this form. And I'm considering this as an estimator for f of x naught. So I can Taylor expand this part here. Okay, so again, I'm going to do a Taylor expansion here. Okay, and this time in the notes, I did, or this is minus sh. I'm going to expand it, but I did more terms. Okay, so f prime of x naught. So this is the difference between x naught minus sh and x naught. So this is minus sh. Okay. So I expanded it out, actually, R terms. This could be S squared H squared over 2. So I'm using, you know, Taylor expansion here to write it this way. And then, you know, so then this would be like the third derivative. Of course, every time I expand it more terms, I'd be assuming these derivatives exist. This is 3 factorial minus sh to the third. Okay, I'll just do dot, 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 because I wrote it in a generic way in the notes. That we have R terms, okay, minus sh raised to the R, okay, and then this is one way of writing it. Like I could have stopped here and put x bar, okay? Like that's one possibility, but this is another way of writing it. Whenever R prime, where I put, because the last term always has to be x bar. Okay, this could be x bar minus fr x naught. Okay, and this is minus SH to the R. So notice this term and this term are the same. So I kind of like added it and subtracted it. Okay, so the reason for doing that is when you analyze the bias, sometimes people put restrictions on this. Okay. All right. Well, the first thing to notice is when I do the Taylor expansion, so this whole thing would go inside here, okay, because I expanded out this function. All right, so we can write down, I'll leave that up, so I won't erase it. Are we missing a minus sign next? Did I erase that next to HDS? Oh, there was a minus sign, you're right. There used to be a minus sign, but I had the limits of integration like this, you know, because we had to change the limits of integration. And so then you can do we had this before, but then when we can do away with this minus sign and put back the limits of integration. Okay, that's what happened with the minus sign. Okay, so now just this whole thing, this, you know, long Taylor expansion, imagine that being here. Okay, we have to use our imagination for this. So the leading term is going to be f of x naught, and then we've got k of s ds. Okay, so we require that this is 1. So that just means that whatever kernel weighting function we use, it needs to be a proper density. It has to integrate to 1. Okay. Now the second term is f prime of x naught, k of s ds times h. Okay, let's see. Oh, there's a minus sign too. So this times h. Well, h doesn't depend on us, so we can take that out. Okay. So symmetry, if we choose k to be a symmetric function, that implies that k of s ds equals 0. Okay. So this is actually the key reason why the symmetric kernel weighting is getting us a lower bias, because normally the bias would depend on h, but because it's symmetric, it like kills this term. They actually call it killing the bias. Okay. So we're killing the bias by choosing a symmetric kernel function. Now the next term is not going to go away usually, but okay, this is going to be like f prime x naught over 2. Then we've got k of s squared ds. Okay, so this is usually not equal to 0. Okay, and then we've got these additional terms. Okay, so in most applications, we have this term. So usually the bias is h squared. So before the bias was h. So remember, h is going to 0. So h squared is smaller than h, because you can think of h as like a small number, like 0.1. So h squared is smaller than h. Okay, so if we can get rid of this term, this usually is a smaller term. Okay. There is a literature that uses kind of unusual kernel functions. So you can actually find some kernel functions in the literature where this would be 0. So they have some kernel functions that kind of look like, they have to go negative sometimes, you know? Because see, this is always positive. So to integrate to 0, this would have to be negative. Okay. So usually people don't use that in empirical work because nobody wants to get a negative density estimate. Okay. that would be really strange. Say the density is minus 0.1 or something, right? But sometimes in theoretical work, like in econometrics, they might need to have a very small bias. Because actually, so modern econometrics, the reason I'm like going over these estimators is there are a lot of other estimators, and there's a whole family of models like that are semi-parametric models. And some of them use these estimators as building blocks for other estimators, okay? And sometimes in that literature, you might need to have a small bias, you know, and you could get the small bias by choosing some unusual kernel function. But usually we would just choose symmetric, and otherwise this would not equal 0. So usually this is the bias, okay? What I did in notes, I did do it for the more general case where I wrote it in a generic way, I guess. I mean, maybe I should have kept it to the simpler case, but I see that I did write it in a very generic way. So, and then I derived out the asymptotic mean squared error for the like general case. So by general, I just mean, you know, maybe you might have more terms. So if you were able to kill the bias for more terms, you know, you could get the bias down to h squared, or sorry, h to the r. Like if you had k of s to the r ds equals 0 or equals 0 for little r equals 1 to cap r, you know, but that would require using like a strange kernel. They call them bias reducing kernels. It's just they have kind of odd shapes. Bias reducing kernels. So if you used a bias reducing kernel, you could get the, you know, the bias to be small. And then the other assumption that you can make is called a, I wrote those here. I mean, maybe I should do it a little less generally because I don't want to overwhelm you all, but you can do an assumption which is called a Lipschitz condition on this f. This is the rth derivative of f. So we could assume that the rth derivative of f satisfies this. Okay. If this is not crystal clear, don't worry about it, okay? I'll just, since it's in the notes, I kind of want you to, this is the last term in the remainder. Just be able to understand the notes. Okay, this is a Lipschitz condition. Okay, and so, and if this is less or equal to h, then you can actually drive the bias to be like h to the r plus 1. So some constant term times h to the r plus 1. Okay. So, but usually we only do it up to here. So usually the bias is h squared. Okay, usually the bias is not, usually we would not be doing this. This would only be like theoretical econometricians deriving out some proofs. If they needed to have a small bias, they might do this, okay? But practical, I mean, I'm more of a practical person that actually uses these estimators with data. So I would normally not use a strange kernel function. I would use like a bi-weight kernel, normal kernel, like I told you. So let's look at the choice of bandwidth. Oh, well, it turns out, so the main message to get out of this is that symmetric bandwidth, you know, around, they call it symmetric binning, but having a symmetric kernel, like around the x naught point, lowers your bias, Okay, so I hope you can see that because this term goes away. That's the key thing because this equals 0. Okay, so you want to choose a kernel function that satisfies this equals 1 and this equals 0. Okay, let's see. So increasing R leads to decrease in bias. Yes. So the reason is that, see, H is a small number, so H is bigger than H squared. So H to the R, where R is large, gets smaller and smaller. Okay. It's because H is shrinking. H still has to shrink to 0 asymptotically. So yes, it does decrease the bias. Well, it turns out I wasn't going to derive this, but you can derive using the same techniques. It's not hard. You'd be using the same like Taylor expansion. So, maybe you might try it just to, it's using similar techniques as for the histogram estimator, but the bias, it does not improve bias. So the symmetry, does not improve variance. It only improves bias. Okay, so if you want to derive out the variance, it's still going to be 1 over NH. So for the variance to shrink to 0, you need NH going to infinity. Okay, so there's no improvement in variance. So it probably would be a good thing, like if you wanted to just derive out something on your own, that's not explicitly in notes, you could try to do the variance for the general kernel estimator. Okay. All right, and then we only have a few more minutes, but you'd also choose the optimal bandwidth the same way. So minimizing the mean squared error. Okay, so you get these constant terms, and the bias is like H to the R. It could be H to the R plus 1, like if you assume the Lipschitz condition. So the bias squared is going to be H to the 2R. Okay, so usually this is, let's see, and what I would do, R is normally 1, but I impose a Lipschitz condition, so it's normally like 2, let's see, 2 times R plus 1. So this is normally 4 for what I would do, okay? But I wrote it in more general terms here. Okay, and then you just minimize this over H, take the derivative, and you get H squared equals, I'll just write up what it is just because we don't have that much time. Okay, so this is 1 over 2 R plus 1 times n to the minus 1 over 2 R plus 1. Okay, so it depends on, your assumptions on the kernel function. You see how choice of kernel matters. So if you choose a kernel that has a lot of these derivatives equal to 0, for a large R, then you get a lower bias. So your optimal choice of H would depend on your kernel assumptions. But usually in the work I do, this ends up being n to the minus 1/5, actually. Okay, well, next time we will show, there's kind of a famous result about that the mean squared error, like the mean squared error can never approach the parametric rate. So next time I'll go over that. That's kind of a famous result in statistics, that non-parametric estimators, they're slower than parametric methods. Okay, so that's a key trade-off. Like you might think this is strictly better because I'm not imposing a density assumption, but actually in terms of precision, the mean squared error always converges below the parametric rate. Okay, so parametric is faster. So normally you get greater precision with a parametric estimator. Okay, so that's kind of the trade-off, but we'll talk about that next time. Okay, so in terms of the data set, I guess that there's some missing values maybe for some of the variables. So I'm going to check with Gabriel exactly like how many are missing. So we might do a new data set and just exclude the missings. So I will get back to you on that. You know, so just, I don't think there are a ton of missing values, but I just have to check with her. And if you have questions or something, you know, just feel free, send me email. You know, I'm just stuck at home all weekend too, as we all are, so I don't really have any big plans. You know, so I'm happy to talk to you if you have questions, you know, about anything related to the data or what the assignment is. Check out those additional notes that I put up about the generalized Roy model. You know, so that should be pretty close to the framework that you use. You know, that's why I put up the notes, so that you would kind of have the model written out. All right, any last questions or comments? Just unmute yourself if you have any comments or questions. Okay, and so in terms of, you know, reading, I would just go through the notes, you know, try to get an understanding of how these like Taylor expansion techniques. Keep an open mind, because I know it's like new, okay? So it always takes a while to absorb new things. Although young people are much faster than older people at learning new things, so you have an advantage. Okay, and then we'll see each other Monday. I have office hours, and then so. But you're free to, you know, contact me at other times too. So have a good weekend, everybody. And I'll see you Monday or Tuesday. Okay. All right. Bye. All right. I forgot to. Alan? Alan.